Now we have the second lecture magistralis by Professor Martin Rees. Please. Arriba. Okay.
Okay. Well, let me say what a privilege it is for me to be here at this conference, and especially as the founder of these conferences, Ray Ruffini, is one of my oldest friends, and we are both just about old enough to remember the 50th anniversary of relativity, which was in 1965. By then, relativists had developed beautiful mathematics and great insights, but the topic was still separate from the mainstream of physics and astronomy, because the gravitational effects in ordinary galaxies and stars are very well described by Newtonian theory, and relativity is just a tiny correction. And of course, at that time, we only had tests of GR with 10% precision, the classic solar system tests in the weak field limit. The 1960s were transformative. On the theoretical side, we had the Kerr solution, the singularity theorems, the no-hair theorems, etc. But in parallel, there were observational breakthroughs too. And I want to say something about those because we're also celebrating the Year of Light. And quasars were the first breakthrough. In 1973, these hyperluminous beacons in the centers of galaxies were discovered, compact enough to vary within days, but vastly outshining their host galaxy. And Martin Schmidt was the first to realize, therefore, that galaxies contain more than just ordinary gas and stars. And this something we now know is a huge black hole lurking in the centers, but it took about 10 years before that was clearly appreciated. But quasars were a key stimulus in the emergence of relativistic astrophysics. But there were others. In particular, a surprise was the detection of neutron stars. The Crab Nebula here is one of the best known objects in the sky. The expanding debris from a supernova witnessed by Chinese astronomers in 1054 AD. But it was a long time puzzle what kept it shining in blue light. And the answer came when it was discovered that looking in the center, one of the little stars there was not an ordinary star, it was actually a neutron star spinning 30 times a second, generating the blue light and sending out pulses. And in neutron stars, the relativistic effects are 10 or 20%, not merely a tiny correction to Newtonian theory. Some stars end their lives as black holes, but these black holes are only detectable if they happen to be in interacting binaries, where they're lit up by the energy released by accretion from their surroundings. And during the 70s, a number of these were found, and the ones of low mass were neutron stars, giving periodic flickering. The ones of high mass were non-periodic, and they were the black holes. This is Riccardo Giacconi. He's had a lifetime of achievement, including the discovery of the first stellar mass black holes. But if history had been slightly different, he could have discovered neutron stars as well, because it could have been that the X-ray binaries were discovered before radio astronomers had discovered pulsars. So he was a lucky man, but not as lucky as he might have been. Quasars are especially bright because, as we now recognize, they're energized by emission from magnetized gas swirling into a central black hole. And it's these same processes which can generate the jets, which we now know inflate the giant radio lobes surrounding some galaxies. A short sociological digression. In the West, and we're thinking back to an era when the Iron Curtain was almost impermeable, the inspirational guru for relativistic astrophysics was in the United States. Here, John Wheeler. And in the UK, Roger Penrose and Dennis Sharma. And in the Soviet Union, Zeldovich led a powerful group of theorists who progressed in parallel with the West. And there were, of course, groups in the rest of Europe and indeed in Japan. I just show these as the highlights. And it was the 1960s which saw one of the first real advances in understanding black holes, the last advance since the work of Oppenheimer in the 1930s, because Oppenheimer and Schneider, in a classic paper, clarified the nature of what happens at r equals 2m in the Schwarzschild metric. And it's interesting to conjecture how much of the work of the 1960s Oppenheimer would have preempted if World War II hadn't broken out on the very day in which this paper was published in Physical Review. Turning now to cosmology. The standard Freeman and Lemaitre models were known since the 1920s, but until the 1960s, astronomers had no instruments really powerful enough to discriminate among them. Indeed, the steady state theory, where there was an infinite past, was still being debated. And here's a picture of Hoyle and Lemaitre, I guess, debating it. Quasars transformed this. Because they're so luminous, they allowed astronomers to probe back far enough along our past light cone to see how the universe was changing as it aged. So a word about quasars and first the galaxies themselves. This picture shows thousands of galaxies from an optical survey and how they're grouped into clusters. But how much can we actually understand about individual galaxies, like this, Andromeda, or like this? Physicists who study particles can crash them together in accelerators and see what happens. We can't crash real galaxies together, and any changes in them typically happen on very long timescales of billions of years. But we can do experiments in the virtual universe of our computer. And this shows a picture of what would happen if two galaxies collided. Everything in each galaxy exerts a gravitational pull on all the dust and gas in the other, and you end up with this sort of train wreck where two galaxies merge. And this will happen, incidentally, to our galaxy in Andromeda in about 4 billion years. And when we look in the real sky, we find systems like this, colliding galaxy pairs. And we'd infer that these two galaxies, one raising tidal plumes on the other, have got dangerously close, and they are in the process of merging. We can do these simulations like I showed, making different assumptions about the mass of stars and gas, and see which matches the data best. And of course, importantly, we found by this method and others that all galaxies and clusters are held together by the gravity not just of what we see, but they're embedded in the dark matter, a swarm of particles of unknown nature, but which collectively contribute about 5 times as much mass as the ordinary atoms. There are many lines of evidence for the dark matter. I've listed 3 of them here. But the last on this list is the one that would most have interested Einstein, gravitational lensing. In this picture, the bright galaxies are in a cluster about 1 billion light years away. The faint galaxies are several times further away still. And you see the distortions indicating that there is gravitational lensing, like from a Pauli figure converging lens, and by inverting the optics, one can infer that there is dark matter in the foreground cluster. And there's something else at the center of most galaxies. There's a dead quasar, a quiescent massive black hole. And indeed, we know that these galaxies now are found in all but the smallest galaxies. Moreover, there's a correlation between the mass of the hole and that of the host galaxy. Not a very good one, but you see it here, and the correlation is not with the entire galactic mass, but with the mass of the bulge. That's why our galaxy, which is mainly a disk, has a rather small black hole in its center, but here are some pictures zooming in on the center of our galaxy, where wonderful observations by two groups have shown the orbits of stars moving around a point mass of about 3.5 million suns. When Andromeda and our galaxy merge, as they will in 4 billion years, the black holes at the center of each will spiral together, forming a binary, which will shrink by emitting gravitational waves and create a strong chirp when the two merge. And there are mergers going on all the time, and the consequent black hole coalescences are the prime events that LISA-type space gravitational wave detectors would be able to monitor. Black holes grow by mergers, but they also grow by accretion of gas, which is what makes them conspicuous. And this process of accretion is surprisingly complicated, and there's a classic paper by Secure and Sunyaev in the 1970s who already highlighted the problems of the angular momentum problem and the radiation pressure on disks. We also know that black holes swallow entire stars. They tidally disrupt a star. I wrote an old paper on this. There's been lots of activity recently, and the tidally disrupted debris swirls down into the black hole. And this is a especially good process to produce flares of radiation. And as Blanford and Nayak pointed out, energy can be electromagnetically extracted from a spinning hole. And this is a especially good way to produce the ubiquitous jets. The Blanford-Nayak process, of course, depends on the black hole spinning. So, how fast are black holes spinning? We have some evidence. The gas swirling into the hole emits radiation, mainly in the X-ray band, produces X-ray lines. And these lines are smeared into a very broad spectrum. If you had this Newtonian theory, you'd get a blue wing and a red wing, but the aberration makes the blue wing stronger, and then the gravitational redshift smears it out. So you expect to see a line rather like the bottom picture here, and the spread of the red wing depends on how close the disk gets to the hole, and it gets closer in a Kerr black hole and a non-spinning black hole. And this is an example of an X-ray observation of the iron line from a quasar, and this is from a Japanese experiment, and this indicates that the black hole involved here must be spinning and can't be just a Schwarzschild black hole. But we don't yet know the distribution of spins. What we do know is that they are all describable just by the two parameters, mass and spin. And this is something which Chandrasekhar thought was rather wonderful, the fact that throughout the universe there are these objects which are described by exact equations that we understand. Quasars are very bright, so we can look back a long way, and this is the most distant quasar with a reliable spectrum. It was found about 4 years ago, and I just show this as the spectrum. This is the optical spectrum, but the main point is that the Lyman alpha line, normally in the UV at 1216 angstroms, is on the left here in the near-infrared, stretched by a factor 8.1 by the redshift. So we can infer that some galaxies had already formed, and accumulated huge black holes in their center to produce phenomena like this, even at high redshifts. But how much further back can we go? We want even brighter objects. Galaxies can be detected slightly further away if we use nature's telescopes and look behind a cluster where they're lensed, but also gamma-ray bursts are powerful enough that we can detect them. And this on the right here shows a sort of race towards high redshift. It was initially just like quasars, now we have galaxies, and we may have gamma-ray bursts going still further out. And gamma-ray bursts outshine an entire galaxy by a factor of 1,000,000, and finding even one of these at a redshift of, say, 15 would be a valuable clue. A clue to when the first structures formed in our expanding universe. But, of course, it's the microwave background which is the crucial fossil of the earliest eras. Discovered just 50 years ago by Penzias and Wilson, and its thermal spectrum, established subsequently, is the most compelling evidence for the Big Bang and has helped us to firm up the familiar time chart of the various events during an expanding universe. Even by 1970, we had precise calculations of nuclear synthesis during the first 3 minutes, when the temperature was about an MeV, about 10 to the 10th degrees. And now we famously have angular fluctuations. The most recent and best have come from ESA's Planck spacecraft, which gave us this wonderful map of the sky, where the fluctuation amplitudes are only about 1 part in 100,000. But the spectrum of these fluctuations is very well pinned down. And these slight ripples, over densities detected at 300,000 years after the Big Bang, they consequently enhance their density contrast and condensed out as the universe expands. The overdense regions lag behind more and more, and this is a movie, a simulation, where the expansion is subtracted out, and you see the density contrast growing as time goes on in gigayears towards the center. And here's another picture which shows separately the dark matter and in blue and the baryons in red, and you see this is how a galaxy forms. The dark matter agglomerates together, and then the gas lights up. In those movies, which I show, these two, it's important that the initial conditions are not arbitrary. The initial conditions are the ones in effect from the Planck spacecraft. And what is a great success is that if you take the fluctuations we observe and run them forward, you find that you get structures where delta over rho as a function of scale fits the observations. The solid line is the observations, it's a theory, and the various kinds of observations which fit this. So we have a gratifying link between what happens at 300,000 years after the Big Bang and the present-day structure of the universe. And we're vindicated, as I mentioned, in extrapolating back to 1 second nuclear synthesis, and probably we could be confident back to about a nanosecond. That's when the average particle had the kind of energies that can be simulated in the LHC. And the entire visible universe would then be squeezed down to the size of our solar system. But questions like, what caused the fluctuations? Why does the universe expand the way it does? Why does it contain the observed mix of atoms, radiation, and matter? These questions can't be answered unless we go back to the even briefer instance when the universe was hugely more compressed still, when experiments offer no direct guide to the relevant physics. And for more than 30 years, we've of course had the inflationary paradigm, which seriously invokes an era, 10 to the minus 36 seconds, when the Hubble radius was 1 billion times smaller than an atomic nucleus. A really astonishing extrapolation. And it's argued that inflation gives the best explanation of the flatness. Moreover, the Gaussianity of the fluctuations seen by Planck and the tilt of the amplitude is consistent. And we'll hear from experts on this later in the week. Turning now from the early history of the universe to its future, we had a big surprise about 15 years ago. It was by then well known that the gravity of dark matter dominated that of baryons, but that the total of those two was about 30% of the critical density. So it seemed likely we were in the middle universe here, one that decelerates but never turns around. But rather than slowly decelerating, the Hubble diagram of type 1 supernovae famously showed the expansion speeding up on the right hand. And this picture shows the Hubble diagram, and later data confirms that this is a better fit. But I wanted to mention that there is independent evidence for this picture. And it comes from studying the microwave background and the curvature. This is the data from Planck, which plots the amplitude as a function of scale. And this is a wonderful combination of theory and observations, because the solid line is the theory, the best fit of a 6-parameter model, and the data points fit it exactly. This is a wonderful triumph. But the major peak here, the Doppler peak, this is something which is a sort of rigid rod. This is the particular scale where the amplitude of fluctuations is largest. And the angular scale on which this appears therefore depends on the geometry. And where it appears is consistent with a flat model. And I want to emphasize this since our chairman here, Dr. de Bernardis, he in effect discovered this, because the balloon ball experiment called Boomerang, of which he was the PI, discovered the Doppler peak, and what it showed was that the Doppler peak had the angular scale indicative of a flat universe, whereas had there been a universe of just omega of 0.3 and nothing else, it would be smaller. And so we have this network of arguments here. If we have omega of 0.3 but a flat universe, then the other 0.7 must be in an unclustered component. Moreover, that unclustered component can't have dominated in the past, otherwise it would have stopped galaxies forming. So it must have a negative pressure. And in Einstein's equations, for the Friedmann models, it's rho plus 3p over c squared that comes in. So negative pressure, which we infer, implies acceleration. So, in effect, from the data from Boomerang, one could have predicted the acceleration. And this came at about the same time. And I personally think that the whole story is only compelling when we tie together the microwave background with the supernovae. If we just had the supernovae, I don't think anyone would be quite so convinced that we did live in an accelerating universe. And an accelerating universe is, of course, something which is a remarkable discovery. It implies that there's some energy latent in empty space, and it's the kind of thing which perhaps string theorists will be able to solve, but only when they can study the nature of space and its graininess on the Planck scale. And now for another fundamental question. How large is the universe? How large is physical reality? We can see a finite volume out to our horizon, a shell around us delineating the distance that light can have traveled since the Big Bang. But that shell has no more physical significance than the horizon around you if you're on a boat in the middle of the ocean. So there are probably galaxies far beyond our horizon. Indeed, almost all astronomers would suspect that the galaxies go several hundred times further. That's because if you look as far as you can in this direction, the gradient's no more than 1 part in 100,000. So if we're part of a finite structure, it goes on a very long way. But it could go on so far that all combinatorial options are fulfilled, and we all have avatars way out beyond the horizon. But that's not all. This would just be the aftermath of our Big Bang. But of course, there are versions of the inflationary model which, depicted by this sort of cartoon, suggest that our Big Bang is not the only one. This is a cartoon of the so-called eternal inflation model, which is due to Andre Linde, and it's one of many models in which the aftermath of our Big Bang could be just one island of space-time in an unbounded cosmic archipelago, just depicted in a cartoon way here. Well, in regard to scenarios like this, it's a challenge to 21st century physics to answer two questions indicated by this decision tree here. First, are there many Big Bangs or just one? Second, this is even more interesting, if there are many, are they governed by the same physics as ours or not? Or is there, as some string theorists suspect, a huge number of different vacuum states leading to different microphysics? If the latter is the case, the right hand of the decision tree, there'll still be underlying laws governing the multiverse, maybe string theory, maybe something else, but what we traditionally call the laws of nature will be just local bylaws in our cosmic patch. And though it makes some physicists foam at the mouth, we can't avoid the A word, anthropics, because many of these domains, governed by different laws, will be stillborn or sterile. The laws prevailing in them might not allow any kind of complexity. We therefore wouldn't expect to find ourselves in a typical universe, rather we'd be in a typical member of the subset where an observer could evolve. Now, this is speculative science, but some go further and say that these unobservable entities aren't part of science at all. But I don't think many people really think that. For instance, we're an accelerating universe, and we know that galaxies we can now see will disappear over the horizon and become inaccessible. But no one surely doubts that there are galaxies beyond our horizon already, which we can't see now and will never ever see. But no astronomer would deny that those are part of physical reality. Those galaxies are part of the aftermath of our Big Bang, but why should they be accorded higher epistemological status than unobservable entities that are the aftermath of other Big Bangs? So it's surely a genuine question to ask whether there's one Big Bang or many. If there's just one Big Bang, then we'd aspire to pin down why the numbers describing it have the values we measure. We use data to get the fundamental numbers, and then we try and make some sense of it. But if there are many Big Bangs, then physical reality is hugely grander than we've envisaged. It could be that in 50 years' time, we'd be just as flummoxed as we are today about the ultra-early universe. But on the other hand, it could be that there will be a theory of 10 to 16 GeV physics which gains credibility by explaining things we can observe and which predicts a multiverse and in principle determines some of its properties, the probability measure of key parameters, the relation between them, etc. And there would be actually an intellectual and aesthetic upside if this was the case. If we're in a multiverse, it would be a fourth and grandest Copernican revolution. We've had the Copernican revolution itself. We know that there are zillions of planetary systems around stars in our galaxy, zillions of galaxies in our observable universe. But the realization that our Big Bang is a tiny fraction of reality would be another big breakthrough. Some people don't like this, as I said, but our preferences are irrelevant to the way physical reality actually is, so we should surely be open-minded about these prospects. About 10 years ago, I was on a panel at Stanford where we were asked by someone in the audience how much we would bet on the multiverse concept. I said that on a scale, would you bet your goldfish or your dog or your life, I was nearly at the dog level. And then Andre Linde, who was on the panel and had spent 25 years working on eternal inflation, he said he'd bet his life on it. But later, Steven Weinberg said he'd happily bet Martin Rees' dog and Andre Linde's life. Well, Andre Linde, my dog and I will all be dead long before this is all settled, but it's speculative science, exciting science, and it may be true. In my final 2 minutes, I want to conclude with a few comments which are addressed to the students and postdocs here. The 1960s were exhilarating for young astrophysicists when so much was new, and the old guys didn't have a big head start over the young ones. But we shouldn't be nostalgic, because today is an equally good time for young researchers. The pace of advance has crescendoed rather than slackened. That's because we have new instrumentation, new facilities like the ones shown here are coming online. And we also have new theoretical techniques. And of course, armchair theory doesn't get you very far by itself, but is now aided very much by computing. And computers have made huge advances recently in these 4 areas, but let me highlight the first one, which is more familiar to people here, which is doing strong field general relativity, being able to actually calculate the waveforms when black holes collide and merge. So I think with a combination of new exciting observational techniques, firming up details of the microwave background, how the universe evolved, and the extreme phenomena in it, and the ability to not merely observe them but compute them, is going to make this an exciting future decade for young researchers. So let me leave you all with that optimistic thought. Thank you very much.
Thank you so much for this magistralis lecture. And we have time for a few questions. Is there any question, please? Well, you should go there.
Yeah. Yes. Or shout very loudly.
Doesn't the homogeneity of the microwave background limit the number of multiverses? It's so homogeneous that if there were large bubbles coming up from other multiverses, they would collide and affect our...
Yes, I'm not an expert. I think that is true of some versions, but I think the ingenious theorists who devised the multiverse model can get round that and ensure they can survive any observational test. So I'd like to reiterate that I think the multiverse idea will be put on a serious footing only if we have a theory which tells us about the inflaton or about the early universe, and a theory that could be tested in other ways at low energies. Because we don't need to be able to test all the consequences of the theory, we need to be able to test some. For instance, in relativity, we believe Einstein's theory about the interior of black holes because we can't observe it there, because we've been able to observe and test the theory in many other places. So we believe in unobservable regions because we can test in observable. And we haven't got to that stage yet, but if we ever did, then we'd be able to answer your question.
Okay, we have time for another question, please.
Martin, thank you for this wonderful lecture. Since you have looked at this astrophysics and cosmology for such a long period, what do you think is likely to shatter our views of the universe, of the world, by a discovery that would happen in the next 10 years? What would you consider to be the most exciting potential discovery in the next 10 years or so?
Well, of course, I'm an astrophysicist, so I hope very much we will learn more about black holes and how they're spinning and how they grew, and about gamma ray bursts and the physics they involve, which is very extreme physics. But if you're thinking about the exotic side of cosmology, then obviously the tensor modes in the microwave background are going to be crucial in as a further test of inflation and pinning down the era when it happened. And we know that that's been difficult, but within 10 years, that's going to be another indicator, quite apart from the Gaussianity and the spectrum and the flatness, which we already have as consistency checks for inflation. Oh, gravitational waves. Well, I think I mentioned LISA because I think if we had a space experiment that could detect these massive black hole collisions, which would be a clean test of gravity and with very high signal to noise. I'm very disappointed about the delays in a space interferometer. We of course have LIGO, and we know that may detect things within a few years. I think that's less exciting because it can't detect the actual final coalescence, which is mixed up with complicated physics anyway. So I think LIGO will be important input into astrophysics, but I think it won't tell us anything fundamental about gravitational waves.
Okay, I believe we have to stop here the discussion. We thank again Professor Martin Rees.